Hello, everyone. Thanks for coming today. It is my distinct pleasure to welcome Francesca Gandini from Kalamazoo College, who will tell us about Noether's degree bound in the exterior algebra. Francesca.
Thank you for the invitation, and thank you for being here on a gloomy Monday afternoon, at least here in Michigan. And we are in our week 4 of the quarter, so starting to ramp up over here to keep some people out of office hours. But I'm very glad to be here with you all. So here's a bit the plan for today. So I want to tell you a little bit about computational invariant theory, which is really a little bit of a motivation for today. And then we're going to have a little bit of history, Noether degree bound. I'm going to use NDB. Wow, I already messed up my abbreviation in the plan. And some history of the generalizations, and that's going to bring us to the subspace theorem, where we're going to need characteristic 0 for the exterior algebra. And I'm going to talk probably briefly here. This is kind of previous work of mine. And then I'm going to tell you about the connection between invariants and subspace arrangements, and how will we use that to construct invariants. And I'm going to say construct in quotes because it's very computationally expensive. But it's still going to give us the Noether degree bound. Wow, at least I was consistent in the exterior algebra. And I want to tell you a little bit about the future direction, in particular polarization. And that's where, if folks are interested, I really would like to have more people to play around with. All right, so let's get down to business. So what do I mean by computational invariant theory? So what we mean computationally is that the goal, right, the ideal. So ideally, we would like to be able to produce a set of generators for the invariant ring, or a minimal set to generate invariant. So ideally, a set of minimal generating invariants. And this is something that before the advent of the computer era was not something that we really had hope for, because explicit computation require computer power. Now we do have some ways to compute minimal generating invariants for nice groups. So in particular, abelian groups and tori, there is a very quick algorithm. But more general groups, or like very large group, this still is very computationally expensive. So this ideal is really like, computationally expensive. And it is more and more expensive depending on how far you have to go in the degree, right? And so in particular, if we can bound the degree of this minimal generating invariance, it also gives us a better indication, right, of where to stop the computation. And so the second best thing is to get a bound. So what we want, a bound on the maximum degree. I'm not liking all of this pink. Let me just quickly do a little change. It hurting my eyes. So ideally, we would like a minimal set of generating invariants, and the second best thing is to get a bound on the maximum degree. And this bound is called B, or beta, of a generating invariant. As a mean. And in general, the bound will depend on the representation that you're looking at and the group that you're looking at. And so, when we think about the bound, independent of the representation, what we say is that, if W is a representation, then what we would care about is a bound that is independent of the representation. So we think about, what bounds all this BWG, and that's going to be defined as beta G. So we think about all the possible representations of the group. Is there some kind of universal bound, right, on this degree of degenerative invariance for the invariant ring? And for infinite groups, really there is like kind of no hope on this. There is no global bound, and I think Derksen has a few results on this result. But for finite groups, we actually are in luck from the work of Noether. So when you have a finite group, there is this beautiful result, and a proof, I think she said to assume characteristic 0, but this is also true when you have a very large characteristic. So P does not divide the order of the group factorial. So a group has a combinatorial kind of element to it. So that's what we need. So in 1915, and I think some people say 1916, depending on the publication year that you consider, that the bound for any finite group is given by the order of the group. And so that tells you that if you're doing a finite group and you're looking at invariant and minimal set of generated invariants, you can stop your computation once you reach the degree equal to the order of the group. And because this result is so powerful from the computational point of view, there's, people have tried to generalize it to different contexts. And around the year 2000, there was kind of a race to the generalization characteristic P. So a little bit the history here. So around 2000, people, it's more than 20 years ago. Can you believe that? So around 2000, people were working on generalization characteristic P. And there were several approaches. What Derksen thought about, and really for characteristic P here, I mean non-modular case. So we still need that P does not divide the order of the group, because if P divides the order of the group, then the bound is false, right? So the modular case when P divides the order of the group is completely wild. So by characteristic P, I mean no modular case. So the idea of Derksen was to kind of use some of the elimination theory from algebraic geometry to think about this problem in terms of polynomials vanishing on some geometric space. And so what the idea from Derksen is that we can, if we can find a bound on the degree of a vanishing ideal of a subspace arrangement, then this bound will give us also a bound on the generators of the invariant ring. So this bound is also going to give us a bound on beta G. So I'm going to shorten it there. Oh, at least at this point I use NDB. So, and I'm going to talk more about this connection in a later section. So this is what we call the subspace arrangement theorem. Really, what do I call this? Coming soon, I'm just going to say. But just taking me on the word, now there's a connection between the bound on the degree of vanishing ideal subset arrangement and a bound on the minimal, on the degree of a set of minimal invariants. And so now what became what became the key ingredient here to establish a bound of beta G was this subspace conjecture. Which then became a theorem in 2021 with Derksen and Sidman. Wow. Derksen, Sidman. So the original conjecture by Derksen was in terms of the degree of the generators, but then Strumpel suggested to do the conjecture in terms of the regularity. So to make this connection work, we needed, Derksen and Sidman needed to bound the regularity of, need another color. So we wanted to bound the regularity of the intersection of T many ideals, linear ideals, by the cardinality, so by T. And so what's important here is this Ji are linear ideals, so they're generated by linear forms. And so once this was proven, we would add the Noether degree bound in characteristic in the non-modular case. And this was proven in, not 2021, 2002. Wow. So this was proven in 2002, but they were like 1 year earlier, or like the same year, they were sending the papers to each other. They were all closely working on this. But in 2000 and 2001, respectively, two people independently, I'm gonna just say respectively, Fleischmann and separately Fogarty, if I can spell. No, I think the H is there. Fleischmann and Fogarty proved this bound using some wrap theory, using some group theory techniques. And however, the next year, the subspace arrangement conjecture became a theorem, and they also generalized this to the regularity of a family of ideals obtained from linear ideals. So not only you can intersect them, but you can also add up to one form. And so there's a whole class of ideals generated from linear ideals which has bounded regularity. And by the way, regularity, I mean in the sense of Castelnuovo-Mumford. And why would that make sense? Well, if you think about the first step in the resolution, your Castelnuovo-Mumford regularity gives you a bound on the degree of the generators, right? Because that's basically the first difference between the first storm module, the dimension of first storm modules, and the generators. And so if you can bound the regularity, then you can also bound the degree of the generators. And because the regularity is stronger, right, a regularity result carries through for a degree bound result. However, as I was learning about this, subspace arrangement approach to invariant theory, I found the whole theory beautiful, and I was like, there must be some other ways to use it. And so I kind of thought about a different way to generalize this, not in characteristic P. So from now on, characteristic 0 all throughout. But what I thought about is that through the tools of representation theory, maybe we can use the subspace arrangement approach to get results for regularity. So first to get results for regularity in the Xer algebra, and then to get bounds on skew invariant polynomials, which is what I'm going to talk about next. So I'm just bothered about not being sure that that's correct spelling for Fogarty. So I was just checking my notes. Oh, there is no H at all. So it's the issue with Italians. We don't pronounce an H, and then when we have to spell, like, is there an H in there? All right. So let me tell you about the subspace arrangement theorem and how I generalize it to the Xer algebra. So in short, so if you are getting distracted, I'm gonna give you the theorem here. And the version of this in the symmetric algebra is what Derksen and Sigman have proved. So if you consider T linear ideals, so ideals generated by linear forms over the Xer algebra, wedge W, then the regularity, in the sense of Castelnuovo-Mumford again, of the intersection from I equal to 1 to T of this linear ideals Ji is bounded above by T. So the cardinality of subspace arrangement. And let me check my time. I'm gonna say just a few words about the methods. If you heard me speak before, I given several talk about the methods for this approach. But just for completion, I'm going to tell you a few things here. So the idea here is to connect the result in the symmetric algebra to the result in the Xer algebra via representation theory. And so what we consider is ideal functors. So going from just a subspace arrangement, W1 up to WT in some ambient vector space. So this becomes an ideal functor if for a vector space V in this space of vectors of finite dimensional vector spaces, we get a new subspace arrangement, but just tensoring the ambient space VV. So for every V, we can consider this construction. And so now the vanishing ideal becomes a functor on this vector spaces V. And not only is a functor, but then we have a polynomial functor. So the vanishing of this ideal A, or the space maybe I'll just put it down here. So this ideal A, that for HV is the intersection of this vanishing ideals. So this becomes a functor, and it's a polynomial functor. So this is the important thing. And so we can use the representation theory in characteristic 0 of polynomial functors as a representation of GLV. And we can then use a transpose functor to consider kind of the same ideal functor, but now in the exterior algebra. And really, this transpose functor works at the level of polynomial functors. So independent for v that tends, for the dimension of v that tends to infinity. But then once we have reduced the result at the level of polynomial functors, then it still carries through, for a specific vector space. It's possible that when the bound was attained, now it's just going to become a strict bound in the exterior algebra. And just to let you know, the notation, I use this omega for this polynomial functor. So this transpose functor on polynomial functors. That's a mouthful. And the reason why I use this omega is because of kind of this idea that on the ring of symmetric functions, there is an involution, which is usually denoted by small omega. And so here the proposition is that if the character of IAV as, maybe I'll just do it independently from V, just to make it at the level of polynomial functor. So if the character A as a GL representation, just gonna set up, is the sum of A lambda S lambda, and these S lambdas are what we call the sure functions. Then if you think about the character of IA prime, because this transpose factor at the level of polynomial functors is exact, is equal to the same coefficient, the same multiplicity, but now with S lambda prime. And so that's what the exactness affords, that we can literally see the characters. And I've used the notation, I used the nomenclature for this character of IA as the equivariant Gilbert series, because especially in the case, so in the case in which you're looking at a product ideal instead of intersection ideal, you can literally read off the the Tor modules that appear in a in a resolution from this character. So let me maybe write this as a name. So I call this the equivariant Gilbert series of this, of these polynomial functors. And main reason why this happens is that because when we consider the product ideal, so instead of looking at intersection, we look at the product of linear ideals, then these are generated in degree T, which is the cardinality of the subspace arrangement. And so this is actually regularity equal to T. So the regularity is equal to T, and so we can read off the Tor modules from this character. And what I mean by can read off, there is exactly 1 degree, right? When the resolution is linear, because the regularity is equal to the degree of generation, the resolution is linear. And so you just really need to look at which Schur functions appear in a certain degree, and those will correspond to the Tor modules that appear in that degree, in that step, homological degree in the resolution. And so this was kind of my, my previous work in building from, from the work with Derksen Sittman over the symmetric algebra to similar result over the exterior algebra. And what I want to tell you next is how to use this to prove results about invariance. So I want to tell you about the connection between invariance and the subspace arrangements. And there is a 50-50 chance I'm going to misspell arrangements as I write. And so, a dime for whoever fixes all my typos. All right. Let me check my time. I want to make sure that I tell you about the future direction. So I need to keep myself in check. All right, so the first ingredient to see this connection is what I call a group arrangement. So you have a group G and a representation of GV. Maybe I'll say V, a G rep. And I know I called the representation W earlier, but all the literature usually calls the representations V. This V is not the same as the V in the polynomial functors. This is a new V, right? And I think I need to go back to my paper and fix my V's and W's. I was reading through it and I'm like, consistency in notation, that's a real struggle. Especially when you want it to be consistent also with the literature. Good luck. Anyway, so what is this group arrangement? I want to highlight this. So this group arrangement is built out of a representation, and it's going to be the union over all the elements in the group, right? And so you can already see why this works better when you work with a finite group of these spaces. So we're going to take a pair of elements in our representation, but now we're going to act trivially on the first coordinate or the first set of coordinates, and then we're going to act with G on the second coordinates. And so this kind of lives in 2 copies of your, of your representation. And you can think about this a bit as the graph of the representation. Maybe I'll write this. And if we write this as a union over G and G, little g and big G of the spaces VG, right? So each set gives you a G. Then, each of these spaces is defined by a set of linear forms. And I'm going to try to be explicit here just for a second. So if you take, so this is generated by linear forms, so the vanishing. So I of VG is generated by linear forms. And these linear forms are going to come from, so if we pick a matrix for the action of G, so this is a matrix or little g, then the vanishing will happen when g of v is equal to v. So basically, v is an invariant point, a fixed point of the action. And so you're going to have that this vanishing ideals will be given by all these forms of the type yi minus ag times x. So by ag times x, I mean, we're multiplying the matrix ag. I worked hard on trying to get the indices correctly here. For j equal to 1 to n, the ij entry multiplied by xj. And we do this for every from I that goes from 1 to n. All right, and so we get n linear forms for each subspace. So for each element of the group, we get these n linear forms, and then we had to take the union of this spaces, and so on the level of ideals, we get the intersection. And so we have this this ideal for this group arrangement. That's how I called it. So this ideal IA, IG for the group arrangement, which is the intersection over this G and G of the vanishing of these VGs. And so this is intersectional linear ideals. And there are exactly G many of them. Order of the group may. And you see now where you probably can guess where we're adding, you know, the cardinality of this group arrangement is precisely the order of the group, and that's going to give us the bound that we're looking for. We can do a similar construction in the exterior algebra. It's kind of funny to call this a vanishing because they're not real function when you think about them in the exterior algebra. But if you think about them as linear forms, that this totally makes sense. So we can think about I prime of G in the exterior algebra. I want to say another color. As an intersection of linear ideals. So we can talk about ideals generated by linear forms. They don't make as much sense as vanishing ideals. All right, so we have these ideals, and now how do we connect this to invariant theory? And this is kind of where my little constructing invariant theory parenthesis starts. So the main ingredient that we're going to need here is what's called the Gilbert ideal. And in the literature, this was really only defined for commutative algebras, and I kind of created a generalization that works for graded algebras so that it could work for the exterior algebra itself. So if you have, so if your A is a graded, connected, maybe positive graded algebra, and you have G acting on A in a degree preserving way, then you can think about this, we can think about the invariance in each degree. So we're gonna, if I ADG the forms in AD, they are invariant. And then we can think about the maximal, the positively, the forms that are invariant in positive degree, because constants are always also invariants if you have a linear action. And then the ideal I plus G of all the positive degree invariance is what we call the Gilbert ideal. And I have several like kind of cute lemmas in my paper on, how. So I really is to make it an ideal independent of commutative and non-commutative, I should say left Gilbert ideal. But because I'm applying this to the X0 algebra and the ideals are two-sided, this doesn't affect things too much. So this left Gilbert ideal would be the ring multiplied by this positive degree invariance. So all the linear combinations of positive degree invariance with the coefficients in your ring, you get it algebra. And I have several lemmas about this Gilbert ideal and how it can be used, how the Reynolds operator works in this context. And the upshot of all this construction, I was so optimistic, like maybe I'm gonna prove some lemmas. So the upshot of this construction is that if you consider the X0 algebra, which is a graded algebra, you can think about it as the algebra generated in X1 to Xn, modded out by the relation Xi, Xj plus Xj, Xi for all ij, possibly equal to each other. Then if I denote the Gilbert ideal with JG, maybe I'll do this in light blue. And the ideal, the subspace arrangement. So the group arrangement ideal. By IG in this context of the exterior algebra, then I prove a theorem very similar, like there is the same kind of result in the symmetric algebra polynomial ring, that you can take your subspace arrangement ideal and set the y's to 0, or add the linear forms of y to yn, and then you can intersect down to the x's, so you do an elimination ideal. And that's gonna actually give you precisely generators for our Gilbert ideal. And why would we want to even do that, right? So one of the lemmas here is that if you have generators for the Gilbert ideal, which themselves are invariant. So this is kind of a lemma. And this is not that big of a deal to find them invariant because you just kind of apply the Reynolds operator to it. So generators for the Gilbert Ideal that are also invariants, say F1 to FR, are generators for the invariant ring. J, E, G. And so how can we use this constructively? Well, we can compute this intersectional ideal IG. Again, that requires a Grosvenor basis in a ton of variables, right? But we can compute this, this intersection ideal, then we set the y is equal to 0, or we get rid of all the things in y and project down to the ring only in x's. So we do this elimination ideal. And then we get a set of polynomials to which we can just apply the Reynolds operator to get a set of generating invariants. So this is actually an algorithm that over the symmetric algebra, the polynomial ring is implemented in the invariant ring package. We worked on that last year. This is not implemented over the exterior algebra yet. I still have to study more the capabilities in the computations over the exterior algebra in my college too. So I should say this is kind of my elimination ideal. So what is the upshot here? Is that, well, so IG is generating degree as degree bound. Less than equal than the order of the group. And then, you know, adding linear forms plus elimination ideal does not change the degree bound. And then applying the Reynolds operator to get invariance does not also change the degree bound. So I would say RG, Reynolds operator, is degree preserving. And so we still get the same bound for the invariant ring. So we have the invariant ring is generated in degree less than equal than the order of the group. And so this can be used in the exterior algebra to prove this Noether degree bound. So Noether degree bound in the exterior algebra. And you would think that maybe there is nothing to like, you know, maybe the Noether degree bound is true in general, right, for any non-commutative ring. And that's actually not true. And I'm gonna kind of tell you a couple of things to wrap up here. So if you look at this Q algebra, but not the exterior algebra, so we allow for skew commutativity, but not the square. The squares are not sent to 0. So if you look at this algebra F, which is K, X1 to Xn, and we have Xi, Xj plus Xj, Xi. But now we need I different from J. So this is sometimes denoted a -1 skew ring. So here the Noether degree bound does not hold. And this is a result of Kirkman, Kuzmanovic, and Zhang And actually, you can even find a very small example here. I think that this is an exercise if you want to kind of play around. You can even just take two variables, x, y plus y, z, y, x. And you can just take z mod 2, which acts by switching x and y. A set of generating invariants is actually x plus y and x cube plus y cube, because x squared plus y squared is not minimal. Exercise. And so because the minimal variant is degree 3, right? So this fellow here has degree 3, which is bigger than the order of the group 2, this violates Noether degree bounds. However, one of the directions in which I'm thinking about going is with the following corollary. So if you think about the ideal of squares, and you assume this is G stable, you can think about going from an invariant in this Skew algebra to some invariant exterior algebra. And because here the Noether bounded holds, Noether degree bound holds, then what needs to happen is f cannot be square free, because otherwise f bar would violate the Noether degree bound in E. If f violates Noether degree bound, it cannot be square free. So this is kind of the big kind of idea here, or really like the suggestion for my future work, is to think about how does polarization work in non-commutative algebras. So it could be, in a sense, that the reason why we have some forms that violate Noether degree bound in the skew polynomial ring is because we have all these squares and maybe we just need to polarize them, and then that would remove this violation of Noether degree bound. So maybe these are not really minimal invariants if you polarize them enough. And this kind of theory of how polarization will work in non-commutative algebra is suggestive because polarization works well in the exterior algebra due to the GLV action, right, to the representation theory. And if you're interested in knowing a little bit more about what polarization means from an invariant theory point of view, that's definitely something that I really would like to talk about. So in invariant theory, polarization is a GLV action for larger V's. And I'm going to leave this in quote. Basically, you can think about polarization as acting with a general linear group of bigger dimension on what you started, and then taking them and taking some general coefficients and using these general coefficients to find this, this polarization in a sense. And if folks are interested, I would definitely want to talk a little bit more about, you know, connecting more the community algebra sense of polarization to this, you know, representation theory sense, because I've had some conversation with community algebraists, and they seem to have like one specific way to think about polarization. But once you think about it as a GLV action, there is a little bit more flexibility there. So all those different types of polarization that you might have thought about, they're all kind of actions of GLV in a sense. And this kind of frame of mind might actually help, you know, help a theory of polarization, which is a little bit more general than what we usually do in community algebra. So I think that is my time. Sorry if I went a little bit over. And I didn't see any questions pop in the chat, but I'm very happy to talk about. And for more details, this paper is on the archive. I might update it in the next week to just put, of course, when I did a talk, I found some typos, right? But that's what it happens, right? That's how it happens. So if you have any questions, please fire away.
Let's thank Francesca. Questions for Francesca?
I have a question. So I like that example you showed us, I guess, recently, showing this another degree bound can fail. But so my question is, so in completely general sense for some non-commutative algebra, is there any bounds?
I think that the bounds are in terms of algebra actions. So that's the work of Kirpan et al., in which they are rephrasing actions in terms of algebras instead of group actions. Because in non-commutative algebra, that kind of makes more sense. You know, that's the non-commutative version of a group from that point of view. What I'm hoping is that using the result in the exterior algebra, we can still salvage some commutative algebra in a non-commutative setting. Mm-hmm. And in particular, what I'm trying to think about is, you know, symmetric algebra, exterior algebra, these are both quotient to the tensor algebra, right? And so one should think about how to make a general theory of polarization or the degree bound index in the tensor algebra. But things get a little bit trickier there, right? With all the tensor, you have no cancellations. And so I've been trying to think about it, and more folks are interested, then it's easier to think about it. Because on your own, right, the past year has been very hard to work, you know, full disclosure. So I kind of managed to corner harm a few times and talk about these things. And we have computed a few examples, and there are interesting things there. Yeah.
Thank you.
Sorry, I'm gonna talk at you forever if you don't say thank you. But yeah, my motto is like the exterior algebra is non-commutative, but as nice as non-commutative can be, basically.
Thank you.
I agree. Other questions for Francesca? All right, let's thank her again.
Thank you.
Then we can stop the recording.